Arrhenius model. The Arrhenius model was the one that we said on the surface makes the most sense. It's the simplest. In the Arrhenius model, what's the definition of an acid?
It breaks down into
Acid makes what type of ion?
hydrogen.
Hydrogen ions. And in that same model, bases make what type of ion? Hydroxide ions. So if you see a hydroxide, it's immediately a base. And then there was strong acids, strong bases, weak acids, weak bases. If you see a hydroxide in the compound and it's a base, it's going to be a strong base. The only examples of weak bases will not have OH in them. So if you see a base that does not have OH, it has to be a weak base. If you see something with OH in it, it is a strong base. The other model was the Bronsted-Lowry model. It was kind of the same idea, but worded slightly differently. So in the Bronsted-Lowry model, what's the definition of an acid?
One that donates a hydrogen ion.
Right. It donates a hydrogen ion, which we call a proton. Because when you think about it, a hydrogen ion, a hydrogen has one proton, one electron. And when it becomes an ion, it lost its electron. So the only thing that's there is a proton. And so we call it donating a proton or accepting a proton. In Bronsted-Lowry acids and bases, the acid donates a proton, the base accepts a proton. So look at the HI. First of all, do you think it's an acid or a base? Acid. What immediately jumps out at you as an acid? A number of you immediately said acid. Why? It has a hydrogen. What does it not have?
It doesn't have OH.
It doesn't have OH. And so it has hydrogen, which makes it seem like it's an acid. It doesn't have OH, which would make it seem that it's not a base. So this is an acid. Do you think it is a strong acid or a weak acid? Strong. Why? It has an H in it. Some weak acids will also have an H though.
So how do you tell the difference?
If it's an ionic compound, it's strong.
Oh, that's right.
And a strong acid is an ionic compound where the positive ion is a hydrogen. That is a strong acid.
Right.
If you have an H, it's an acid. If the compound itself is an ionic compound, it's a strong acid. If it's a molecular compound, then it's going to be a weak.
So if it contains a metal, right? Ionic contains a metal.
Well, in this case, the hydrogen is acting as our metal. Essentially, what you want to look for is a hydrogen with a halogen.
Hydrogen or halogen.
You see a hydrogen with a halogen, it's strong. What about NH3? NH3 is ammonia. Do you think it's an acid or a base? It's a base. It's a weird base. There's no OH in it. So do you think it's a strong base or a weak base? It's a weak base. A weak base is a base that does not have OH in the formula. So let's look at this one and figure out why it is a base. If we put that into water, what do you think it's going to make? NH3 plus H2O is going to make what? NH4, right. It's going to steal a hydrogen from the water. It's a base. Bases accept protons.
So plus OH.
Yeah. So it accepted one of these hydrogens. One of these went over here to make NH4 and left behind OH negative. So when we put it in water, it made OH negative, but it had to react in order to do it. If we go back up to HI, if I put HI in water, it's ionic. It's just going to break apart into its ions, one of which is hydrogen ion. We go back and look at our sodium hydroxide. Because there's because there's hydroxide in there, when I dissolve it, I immediately get OH. And so it's a strong base. That's a weak base because it had to react with water in order to make our hydroxide. We're going to skip this slide, just cross it out. It makes it more complicated than it needs to be. So, in this case, our acid has one hydrogen. That's what we would call a monoprotic acid. Mono being one, protic meaning having protons. The name monoprotic? No. But some acids have more than one hydrogen. So those we call polyprotic acids because they have more than one proton. These are some examples. This is phosphoric acid. This has 3 hydrogens. Carbonic acid has 2. Sulfuric acid has 2. These acids can give off all of their hydrogens, but each hydrogen is independent of the other. One comes off, then the next one comes off, and if there's a third, then the third comes off. It's not that both or all 3 come off at the same time. So here is a reaction that we see happening. I want you to look at that and figure out which reactant, that one or that one, is acting as our acid and which one is acting as our base.
So H2O is acting as an acid?
Yes. Why did you say that? What does an acid do? It donates a proton, it donates a hydrogen. So that's what happened here. The water gave a hydrogen to that. So one of these hydrogens moved over here to make HOCl and left behind OH negative. What about in this one? What is our acid? What is our base? H2SO4 is our acid. If we look at it, one of the hydrogens moved over here. So it donated it to there. There's an even simpler way that you could have known that that was our acid. How could you have known? It has a hydrogen in it, so it kind of looks like an acid. What's the name of that? That was something we covered maybe a month or so ago in our naming lecture. Sulfuric acid. Sulfuric acid, believe it or not, is an acid. And so if you look at it and you see that, it's not going to be a base. What about here? What is our acid? What is our base?
H2 is the acid, right?
Where is the hydrogen starting and where is it ending up? One of these hydrogens from NH4 is coming over to the water. And so it's going from here to here, so that is our acid and that is our base. And so on this slide we see that water can be both an acid and a base. Up here it gave a hydrogen, down here it received a hydrogen. There are very, very few molecules that can be both an acid and a base, and water is one of them. And so if we come back and look at number 3 here, we see NH4. We said that was an acid. Here we got NH4 from our NH3. So NH3 was a base, but when one put it in water, it actually made an acid. So this is what we call a conjugate acid-base pair. So we're going to use this as our example. In this case, with our reactants, what is our acid? Just like we were doing before. Which one of these two is our acid? Which one is giving up a hydrogen? HF gives a hydrogen over here. So this is our acid. This is our base. The thing that is left over when an acid loses a hydrogen becomes what we call the conjugate base. The thing that is made when the base receives a hydrogen is the conjugate acid. And so here, this was our acid. When it lost a hydrogen, all that's left is a fluorine. And so fluorine is our conjugate base. The acid made a conjugate base. This was our base. It gained a hydrogen to make our conjugate acid. So the type of problem you would see here is a reaction where they want you to label the acid, the base, the conjugate acid, and the conjugate base. But in reality, when you're starting out and you're first looking at it, if you can name one of them, just one of them, the other ones come by process of elimination. So I look at this, and the first thing I pick out the acid. To me, the acids always jump out. It's the thing that loses a hydrogen. So I know that is my acid. By default, that has to be my base. There's no other options, so I'm half done. Then I take my acid, and I say, if I take a hydrogen off of it, what is left? I take a hydrogen off, so I find this one. So that must be my conjugate base. I only have one thing left to name, my conjugate acid, and this is the only thing that doesn't have a name yet. So that must be my conjugate acid. So this conjugate acid-base pair refers to HF and F negative. That's the acid-base pair. And then this and this, because they differ by one hydrogen. A conjugate acid-base pair is one hydrogen different from each other. If you take phosphoric acid, the conjugate base of it is different by one hydrogen. And so we just take off one hydrogen to go down to H2PO4. When the hydrogen leaves, remember it's H+. If the plus comes off, the thing that's left behind becomes negative. Yeah?
You said the acid and the conjugate base are the conjugate acid-base pair?
Well, that is a pair, and that is a pair also.
Oh, so they're both.
Yeah. But with the phosphoric acid, make sure you only remove one hydrogen. There's only one hydrogen at a time. You don't take all three off to get just phosphate ions.
Wait, go back.
Yeah. So if you have a list of acids, we have to write the conjugate base. So remember that the conjugate base is going to be different by one hydrogen. And since these are acids, they're going to give a hydrogen. So what we need to do is we need to take our acid and remove one hydrogen. If I remove one hydrogen from that, what do I have left over?
HCO3.
HCO3. And what is the charge on that going to be? Negative. Because when the hydrogen leaves, the one hydrogen leaves, it takes a positive with it. And so what's left behind is negative. So what is the conjugate base of H3PO4?
H2PO4.
H2PO4 with what charge? Negative, or minus. Ooh, I don't know why. And so if we take another one off, because it's the polyprotic acid, it can lose all three stepwise, we end up with this. But this also has a conjugate base. We take the last hydrogen off, we now have that. What is the conjugate base of NH4 plus? NH3, but what's the charge? Over here, we were starting neutral, 0, and going down to negative. Here, we went from -2 to -3. If we start at +1 and go down 1, where do we end up?
No.
Neutral.
That's right.
Neutral. And so it goes from NH4 to NH3, and the charge goes from positive to neutral. What is the conjugate base of water? HO or OH minus hydroxide ion.
Wait, H is negative.
That one? That negative.
No, just like starting off. Like for HPO4.
This
Why
one?
did it go to -3 again?
Because we started here with a 2 minus. When we, for every hydrogen we get rid of, we have to go one more negative, one more down.
So it's negative.
Correct. Because we started negative, we have to go more negative. Here we started neutral at 0, so we went down to negative. Here we started at -2, so we went down to -3. Here we started at +1, so we went down to 0. We can also do bases to conjugate acids. Again, one hydrogen different, but we're going to add a hydrogen, and the charge is going to go up 1. So what is the conjugate acid of SO4 2 minus? We can add a hydrogen to get HSO4, and we'll go from -2 to -1, up 1. If I add a hydrogen to this, what do I end up with? H2CO3, go up 1, -1 plus 1 is 0.
Oh, I get it. The eight, we did that last time too, because they were acids.
Right.
So we lose.
Correct.
Okay, that's
Yep.
always
Here, NH2, add a hydrogen, go up 1 on the charge. It's NH3, -1 becomes neutral. Add a hydrogen, HClO2, -1 becomes neutral, and then that is H3PO4 neutral.
Can you go back just for a second?
So here's one starting from scratch. We have an entire reaction there. We have to identify the acid, the base, the conjugate acid, and the conjugate base. Like I said, I immediately find the acid. Of these 4 things, which is the acid? H3PO4. The acid and base are reactants. The conjugate acid, conjugate base are products. And so when we're looking for our acid, we immediately have it narrowed down to these 2. And we can see that this gives a hydrogen to that. H3 becomes H2, H1 becomes H2. So a hydrogen is going from here to here. That is my acid.
Wait, you said the conjugates are always products?
Yes. Acids, bases are reactants. The conjugates are the products. So that's
H2CO3 is a conjugate of acid. H2CO3
yes,
is a conjugate acid, right?
yes. So this is my acid. So what is that by default? Base. I said that was my acid, so that has to be my base. If that is my base, and I add a hydrogen to it, I get that one. Does everybody see how if I add a hydrogen to that one, I get that? It's not that one. This one has the carbon in it. This one has the phosphorus in it. So that one becomes that because that was the base. That must be the conjugate acid. The base makes the conjugate acid. This was my acid. When it loses a hydrogen, it becomes that. The acid makes the conjugate base.
I think this is easier than that, in the date last time. Wait.
Okay. So we're going to talk about solutions now. Not just this compound is an acid or a base, but they're only really acids and bases when you dissolve them in water. So we're going to talk about acidic solutions and basic solutions. So a neutral solution is one where the H3O plus is equal to the OH minus. And remember what H3O plus is. It's essentially a hydrogen ion. But this doesn't actually exist in real life. When you dissolve an acid in water, it makes that, but it immediately reacts with water to make H3O plus. And so we take the H, so H2 to H3, and the plus comes over here, so we make H3O plus. That's called hydronium ion. So you can treat H3O plus exactly the same as H plus. They're interchangeable. H3O plus is technically more correct, but if you ever write just H plus, you'll be just fine. So the neutral solution has the same amount of acid as it has base. So it's neutral. Neither of them is stronger. But if we add something to it, so that we then have more of the acid than the base, the concentration of the H3O plus is higher than the concentration of the hydroxide ion. It is now an acidic solution. For this to happen, we had to have added something that gave us hydronium ion, which would be an acid. So if you add acid to water, believe it or not, you get an acidic solution. If the hydroxide ion concentration is higher than the hydronium, it's a basic solution. If we start with neutral water, the only way for this to get higher than that is to add some of that. And if we added some of that, that means we added a base, because bases have hydroxide ion. And so that is a basic solution. But this raises a question. If I take water and I add acid, so I add H3O plus, why is there hydroxide ion in there? And if I take pure water and I add sodium hydroxide, so I am adding hydroxide ion, why is there any hydronium? And if I take pure water, this tells me pure water, which is neutral, has the same amount of hydronium as it does hydroxide, which implies that those two things are present in my water. But why would that be? It's because water breaks apart on its own. If we take water, H2O, it's actually made up of H plus OH minus. That is what water is. That is the very basis of an acid. That is the definition of an acid, H plus. That is the definition of a base. So water has the parts of an acid and the base. If it splits apart, you get some of that, which is H3O plus, and you get some of that. So in neutral, pure water, you have H3O plus, and you have hydroxide. And water does this automatically. We don't have to do anything to it to make it happen. In a beaker of pure water, two water molecules will come together. One will give a hydrogen to the other to make H3O plus, leaving behind OH minus. And a certain proportion of the water in that beaker will always be ionized. The vast majority of it will just be H2O, but some of it will always be ions. And so, there will always be H3O plus and OH minus in there. And they'll always be equal because to make one of these, you also make one of those. It's 1 for 1. You make them both at the same time. And so in a neutral water solution, they are there in equal proportions, and they are both, in fact, there. If we look at the concentration of H3O plus and OH minus in a solution, whether it's pure water, whether we add an acid to it, or we add a base to it, it turns out that this concentration times that concentration is always constant. This times that is a constant, and at 25 degrees or room temperature, that constant is 1 times 10 to the negative 14th. That's a number you'll need to know, but it's a number you'll use so many times that it's probably one of those ones that you'll memorize anyways. And so, if this times this is 1 times 10 to the negative 14th, and in a neutral solution, these two are equal to each other, mathematically, they both have to be 1 times 10 to the negative 7th. That's not something you have to memorize, but that is something we'll come back to. What you really need to remember is that this Kw, the water constant, water ionization constant, is 1 times 10 to the negative 14th.
Were you trying to say what the frequency?
That's just saying this number changes based on temperature. But this is the only value of that number we will ever use. This is just pointing out that that number is technically only correct at 25 degrees Celsius. So remember, this is a constant. Concentration of our acid times the concentration of our base is always 1 times 10 to the negative 14th. If we have an acidic solution means there's more of this than there is of that. Even though to multiply together, they are always the same in an acidic solution, because that goes up, this must go down. In a basic solution, because that went up, this has to go down. It would seem, if you add a base to a solution, yes, that'll go up, but there's really no reason for that to go down. But it does. Because the two multiplied together have to stay the same, if we add a base and that goes up, there's nothing to do for this one but to go down.
And that makes it basic.
Yes. It becomes basic because the OH becomes higher than the H3O+. So, in neutral solution, they're the same. Because they're the same, they both, by definition, have to be 1 times 10 to the negative 7. In an acidic solution, that means the H3O plus is higher than the OH minus. The acid is greater than the base. So the acid concentration must be greater than neutral. It must be higher than 1 times 10 to the negative 7 molar. And if that is higher, that must be lower. in a base solution, the OH minus is higher than the H3O plus. So H3O plus is less than at neutral. OH minus is higher than at neutral. But in all three cases, when you multiply these two together, they have to be 1 times 10 to the negative 14. So, because it's constant, if we know one of the two, we can easily find the other. Because Kw equals H3O plus times OH minus, we can rearrange that. If we solve for OH minus, it says concentration of hydroxide equals Kw divided by H3O plus. And Kw is a constant. It is always 1 times 10 to the negative 14. And so if we know H3O plus concentration, we can very, very easily if we know this one, all we have to do is plug it in here, and we'll get that. If we know the OH minus concentration, we solve for this. So this becomes Kw divided by OH minus. So it's Kw, 1 times 10 to the negative 14, divided by OH, gives us our H3O plus concentration. So here we have our H3O plus. So in this case, Kw equals 10 to the negative 5th times OH minus, and Kw is 10 to the negative 14. So when we solve for OH minus, what we get is 10 to the negative 14 divided by that is 10 to the negative 5. And that will give us OH minus. You can put it in your calculator. Yeah,
Where
question.
did you get negative 10 to the negative 14?
That was, that's Kw, so it's
Oh,
1
that's-
times
okay.
10 to the negative 14,
Okay.
but that 1 doesn't mean anything.
Wait, so what is, I thought, what's the equation actually?
The equation was this.
What? I had it as Kw is 1.0 times 10 to the negative 14.
Correct. So here, I plugged in the acid concentration here. So that's this. So that became that. But we know Kw is 1 times 10 to the negative 14. And so what we got is 1 times 10 to the negative 14 equals 10 to the negative.
What's the H3O plus stuff though? Is that part of the equation?
This.
Yeah. I'm just confused on what the equation is.
So the equation was this. And so we have the three variables, but that one always stays 1 times 10 to the negative 14. And so we'll be given one of the other two, and we just solve for the third.
Wait.
So you can put that in your calculator. 10 to the negative 14th divided by 10 to the negative 5th. But luckily, these numbers you can actually do in your head easily. Because there is enough, it's just 1 times and 1 times. 10 to the negative 14th divided by 10 to the negative 5th. How do you do that in your head?
Subtract
Yes. If you divide an exponent by another exponent, you take the top one and subtract the bottom one. So in this case, we're subtracting a negative, and so it becomes negative 14 plus 5, and so OH minus equals 10 to the negative 9th. If you can't do that in your head, you can always just put that in your calculator, and it will give you 10 to the negative 9th. So the second row is the same idea. The only thing that's different is our H3O plus. So instead of 10 to the negative 5, we have 10 to the negative 12. So what is my OH minus concentration? Negative 14 minus negative 12, and so negative 14 plus 12 is negative 2. 10 to the negative 9. So the last two, it's the same thing again, but we know the hydroxide and we're solving for the acid. And so this is my equation still. I know Kw is 1 times 10 to the negative 14. Right. H3O plus is what I'm trying to solve for. And I know my OH minus is 10 to the negative 6. So I need to solve for that. I get 10 to the negative 14 divided by 10 to the negative 6 equals what? Negative 8. Negative 14 plus 6 is negative 8. So the last row, again, we have negative 12. So if the last, we have 10 to the negative 12, what is the acid going to be? 10 to the negative 2. And so the only thing that changes why are we dividing? This is our equation, right? So this Kw is always that, always. Yeah. And so we know OH minus, it's given to us. And so it's just solve for x. This equals this times that. Here it is. These two are multiplied together. That's an x, not a plus. So, so you're solving for the unknown variable is what you're doing. And so to solve for that, you would divide both sides by that. And so you get 10 to the negative 14 divided by what was 10 to the negative 6. So for the last one, you divide by 10 to the negative 12 to get negative 2.
So either way, you're going to divide because they're both on that side.
Correct.
Of the equation.
So you're going to divide 1 times 10 to the negative 14 divided by the known one to get the unknown one. Once you get comfortable enough with it, you can look at it, and you don't even have to do any of this. You can just look at it and say, my exponents have to add up the 10 to the negative 4, have to add up the negative 14. So here, if this one's negative 12, this one must be negative 2. Because that's what makes negative 14. Here, this one's negative 6. This one must be negative 8. Because that's what adds up to negative 14. -5, -9. Because that's what adds up to -14. That's what you're doing here. It just takes the math actual equations out and just makes it a little quick mental exercise.
Will it always be divided by like 10?
Yes, where it comes in is, in all of these cases, it's 1 times. It won't always be 1 times that. If it's something other than 1 times that, the whole mental math thing goes out the window. If it's anything other than 1 times 10 to something, do not try to do it in your head. Then you have to do it in your calculator. Yes?
Yeah.
Where did that come from?
Yeah.
So that was our known one.
Well,
So this one, yeah, that's left over from this one. So if that is going to be 12, this needs to be 12.
We were probably overthinking it tremendously.
So here we have OH minus concentrations, but they are not easy, simple little 1 times 10 to the something. And so the mental math goes out the window. So here we have to actually do the calculator math. So, but this is always our equation. Kw equals H3O plus times OH minus. So in this case, we know that OH minus is 2 times 10 to the -8. Kw is always this, so I will plug in my OH minus. So I get 2 times 10 to the -8. If I solve for H3O plus, I get 10 to the -14 divided by 2 times 10 to the -8. When you put that into your calculator, it's begging for a wrong answer. If you put in your calculator 10 to the -14 divided by 2 times 10 to the -8, you will get a wrong answer. Because your calculator is going to do that, divided by that, to get a number, and then times that to get another answer. But what this equation is saying is you need to divide by that, and you need to divide by that. So when you put it in your calculator, if you want to go 2 times 10 to the -8, you have to put that in parentheses. Your other option is to use the EE button like we've learned probably the second week of the semester. You can go 2E -8. If you do it this way, it ties those two things together. It's the same as putting the parentheses around it. But you have to do that or that. Otherwise, you'll get the wrong answer out. So if I go 10 to the -14 divided by 2 times 10 to the -8, what does your calculator give you? 5e -7, which is the same as saying 5.
Wait. I didn't get that. I got 5e to the 22nd.
That is, I know is wrong. Did anybody else get the -7?
Yeah.
Okay. Try it again.
Okay.
So that 5e -7 on your calculator is 5 times 10 to the -7. The e means times 10 to the. That's what the e means. And technically, this is molar.
No.
You say, why is it molar? Because these are concentrations, and so this is given to us in molarity. So if we put molarity in, we get molarity out.
I got it.
But you will never use anything other than molarity. So if we do the next one, same equation. All I do is I change my OH minus.
Is that -7 X for the answer?
Yes, it was. Yes.
And you need to put the N in
To be 100% correct, yes.
there?
And so the only thing that's going to change, instead of 2 times 10 to the 8th, I have 0.035. So this becomes 0.035. And what is that answer?
0.0483.
0.0483, like that?
You want the rest of it?
No, that's fine.
Okay.
That's fine. So it's not hard. You just have to learn to put it in your calculator. So this is a more realistic situation because you don't make up a solution and immediately know what the pH is or what the OH minus concentration is. What you know is the concentration of your solution. But it's a very easy step to go from here to this. All you have to do is figure out, is what I'm adding an acid or a base? Is that an acid or a base? It's an acid. That's hydrochloric acid. So if we have 0.1 molar hydrochloric acid, for every one of these that breaks apart, we get one of these. And so, .1 molar HCl will give us 0.1 molar H3O plus. And so you look at that and you say, because that's an acid, my H3O plus concentration is 0.1. So my equation is the same. In this case, I know that one. 10 to the negative 14 equals 0.1 times OH minus. So OH minus equals 10 to the negative 14 divided by 0.1, which gives you 10 to the negative 13. Yes?
Will they always be the same, like 0.1?
Just,
I
we'll,
got the 0.1.
just in case we don't run into that example, I'll cover it now. So let's say, instead of HCl, we had H2SO4, a polyprotic acid. If we had 0.1 molar H2SO4, that would give us 0.1 times 2, 0.2 molar H3O plus.
So it's all dependent on how many hydrogens?
Correct. And so you take the concentration of your solution, in this case 0.1, times however many hydrogens you get. So in this case it's 0.1 times 2. In this example, this is a base.
Would it matter if you had the extra 0 then? Like 0.1 out?
No,
So that's what.
that's just sig figs, which we're not, thankfully, not that worried about at this point.
Okay.
So this is a base. For every one of these, you get one of those. There's one OH in NaOH. And so it's 0.1 times 1 is 0.1 molar OH minus, and then we go through this just like we've been doing. This is the same as that. But instead of 0.1, it's 0.0001. We come back up to our base. There we had NaOH, which just has one hydroxide in it. But if we had something like calcium hydroxide, where there was 2, 0.1 molar calcium hydroxide is 0.1 times 2 is 0.2 molar hydroxide.
Okay, so it's a base behind the hydroxide.
Right. So if your solution is of an acid, it's telling you your H3O plus concentration. If your solution is a base, it is telling you your OH minus concentration. Because acids make H3O plus, acids make H plus, bases make OH minus. So your solution determines one of the two, then the other one changes to go along with it. And so your solution,
Calcium up there, though.
that was an example,
Oh, okay.
like instead of HCl we would H2SO4. There we have NaOH, which just has one OH.
Mhm.
And so 0.1 molar NaOH is 0.1 molar OH minus.
Right.
But here we have two OHs.
I
And
see.
so we went 0.1 times 2 is 0.2 molar OH minus.
So it's the same example as
Correct.
hydrogen.
It's just meant to show that it's not always that number is immediately that number.
So it's going to matter if you have to like tell first if it's an acid or a base.
Correct. So that's the very first thing you would do is figure out, is this an acid or a base? Because that's an acid, this number is telling me my H3O plus number. This one, the first thing I would do is say that's a base. And so this number is telling me my OH minus number.
If it's an acid, it's telling you H3.
So it's going to be
Correct.
H3O equals, right? Or OH equals. Is it OH equals?
For what?
Yeah, OH equals for NaOH.
Yes. And so it would be OH equals 0.1. And then you would solve for H3O plus.
When you're
So you're
solving,
going to do 10 to the negative 14 divided by
0.1.
0.01 or 0.10.
Correct. Yeah, go ahead. That was it. This is something that I think once you get home and you do some examples on your own, you'll realize how simple this really is.
I don't think it doesn't have this.
Say it again?
I hope you put on a quiz after.
No, because the lecture material is always on the next week's quiz, which next week's quiz is an exam. Our last exam is next week.
On Tuesday?
Yeah.
so what happens after that? We don't meet anymore?
We have review, but the week after that, the last lecture, so next week we have the exam, the first half of class, and then we have review. Then the week after that, we have review, and then a quiz at the end. And then the week after that's the final.
So what do I need to study for the exam?
Yeah.
It's everything since, I'll look at it at break. Somebody remind me to go over what's on the exam after break.
Is it all of what we went today?
Yeah. So it's today's stuff, last week's stuff, and then the stuff from after the last exam.
So starting at molarity.
Molarity was on the last exam.
Yeah.
So it's dilutions, colligative properties, whatever we did last week, I don't even remember, and then today. It was equilibrium. We did equilibrium last week. So it's dilutions, colligative properties, energy diagrams, equilibrium, and today.
You have harder stuff for
It keeps going. Were these on your sheet?
No. And the relationships. It says fill in the blanks, but there's no.
On this slide?
It said activity H3O plus and OH negative relationships. And it says fill in the blanks, but I think the box wasn't there with the. Oh gosh, this is long.
Okay. So, we don't have to work in these crazy scientific notation numbers. To make it easier on the eye and less buttons you got to push in your calculator, we change our concentrations into more workable numbers. And so you're familiar with pH. That's an idea that you're familiar with. The way we calculate pH is the negative log of our H3O plus concentration. So if you know H3O plus, you take negative log of it, and that gives you the pH. Now, when you put that into your calculator, there should be a button that says log. This is the log button. It is not the natural log button, which would be ln. The natural log button is ln. That is not what you want. You want one that says 10. It might possibly say log with a little 10.
It says 10 with an X.
10x above.
Yeah.
Like that?
Well, yeah, but no.
Oh, the big X there. That?
No.
No, it's 10 with an X.
With the X.
It's
It's
a
a
different.
different, it's a whole different thing.
Log equals same as 10.
Mine is a,
Oh.
mine says that.
Okay, so the 10x is the blue function button.
Yeah.
Yeah. So you want to hit the button that just says that, maybe just log.
So just
Yeah, just log.
If it just says log, that's it. That's it.
But not ln.
Correct.
And it's going to be negative.
Correct. And so you would go negative, the log button, and then your number. Make sure you use the negative button, not the minus number. You want the negative. And so, if we take the negative log of 10 to the negative 1, does anybody remember what logs do? What's the purpose of a log? Mathematically, what do they do?
The inverse?
The way I think of it, they take an exponent and make them a regular number.
Right.
And so if we have 10 to the negative 1, if we take the log of that, it takes that negative 1 and moves it down here in front. And so what we get is negative 1 log of 10.
I just got one.
Right. So when you did negative log of 10 to negative 1? Yeah. And so if we take negative log, we get negative 1 times the negative log of 10. Log of 10 is 1. And so what we get is negative 1, which is what? long story short, if you're taking the negative log of something like that, just take the exponent and make it positive. 1, 5, 7, 11. Close your parentheses. Oh, also it's 10 to the negative 2 to the negative. And so if you put all of these in your calculator, it just give you 5, 7, 11. That's why this log is convenient. It takes this nasty looking thing and turns it into a 1. 1, 5, 7, and 11. So if this is pH 1, 5, 7, and 11, we earlier learned how to interpret these numbers as acidic, neutral, or basic. 10 to the negative 1, was that acidic or neutral? Acidic, neutral, or basic? Do you remember? So well, let's go down here. 10 to the negative 7 was neutral. That is neutral. Is 10 to the negative 5th molar more concentrated or less concentrated than 10 to the negative 7th?
Do you mind explaining that?
Yeah.
Do you want to know if they're acidic or basic?
We're getting there. So we said this is neutral. 10 to the negative 7th is neutral. In order to figure out whether these two are acidic or basic, we have to figure out whether 10 to the negative 5th and 10 to the negative 1 is a larger number or a smaller number than 10 to the negative 7th.
They're larger numbers.
They're larger numbers. Because they're negative exponents, these are larger numbers. 10 to the negative 7 is 0.000000061 with a 1 there.
So 10 to the negative 7 will always be neutral.
Yes. 10 to the negative 7th is neutral. 10 to the negative 5th is 1, 2, 3, 4, that.
It's going to start becoming closer.
Correct. That number is larger than that. 10 to the negative 1 is that. They're coming closer to 0. Sorry, no, they're coming closer to 1. They're coming closer to 1.
Yeah.
They're coming closer to 1. So that is the smallest number. That is bigger, and that is even bigger. So these are more acidic than neutral. So a pH less than 1 is acidic. pH less than 7 is acidic. pH larger than 7 is basic. And 7 is neutral. So this is a pH range. For the most part, the pH range goes from 1 to 14. But that is not set in stone. The pH range has no end. We will see examples where the pH does not fall in that range. If you do a problem on a quiz or an exam and your answer is outside of that range, that does not automatically mean you are wrong. So if we look at this, in this column we have hydrogen ion concentration, and then in this column we have the pH that goes with it. 10 negative 14 is 14. We just take the exponent and make it positive. Okay? And these are examples of things that are those pHs. Pure water is 7. We'll see in lab, when you get water out of the tap, water that we act like is pure, you will not be 7. There are other things in there. Some things are acidic: milk, rainwater, beer, vinegar. Stomach acid is about a pH 1. Basic: ammonia, sodium hydroxide. Most detergents are basic. You need to remember, so let's just do this first. So it's asking what is the pH of 2 molar HCl. The equation for pH, remember, is negative log of the hydrogen ion concentration. So we need to figure out the hydrogen ion concentration. We have 2 molar HCl. What is the concentration of my H3O+? 2. This is an acid, so this number is telling me my acid concentration. With just 1 hydrogen, so it's 2 times the 1 is still just 2.
Telling you that H3.
Correct. And so it's telling me my H3O+ equals 2.0 molar. So I need to take negative log of 2. And what is that? 0.3 is my pH.
So it's negative. Is that right? On my calculator.
Yes.
It's -0.
Yes, that is right. The pH is negative 0.3. That is not in our 1 to 14 range. But it is correct. That 1 to 14 range is good for everyday things, but when we get into lab, we go way out of that range. This is 2 molar HCl, and it's already well out of the range. The bottle of hydrochloric acid that the stockroom uses is 16 molar. So it's even more negative. The sulfuric acid bottle that they have is probably 12 molar. But sulfuric acid is H2SO4, and so that bottle has 24 molar H3O+. And so that pH is really, really negative.
What if they give you an acid?
They give you a base, there will be examples of it. We'll get there.
So this is like, this would be like lemon juice? What would this be? Like pH equals 0.03.
We're off the bottom of the scale.
Oh, we're off the bottom.
Yeah, because the bottom is 1 molar HCl, what we have is 2 molar HCl.
Oh.
So we're off the bottom. And what I was getting at before I saw that last question was you have to remember what this pH scale means. It's a log scale. It's a log base 10 scale. So if we look at pH 8 and pH 9, these are the concentrations of H3O+ that go with them. So, by what factor are these two different from each other? How much larger is that one than that one? In pH, it's 1. In concentration, 10 to the negative 8 is 10 times larger than 10 to the negative 9th. So when you go by one number on the pH scale, the acid concentration is actually 10 times higher. And so a pH 1 is 10 times more concentrated than a pH 2. And the reason they do that is it allows us to get this huge, huge range within a convenient set of numbers 1 to 14. If you have a linear scale rather than a log scale, you can't really do pH then. Then you're just dealing with your hydrogen ion concentration, and it's not convenient.
So it would be, you just answer that by 10?
Yes. And so if for every 1 in the pH is a factor of 10, what factor, how much more acidic is that than that? For every 1, you multiply by 10. And so we go from 2 to to 3, we multiply by 10. And then 3 to 4, we multiply by 10. And so that is actually 100 times, 10 times 10, more concentrated than, sorry, that is 10 times more concentrated than that. You're right. This is a lot of 10s.
8 is 10, and then 2 to 4 is 100.
Yes. And so 2 to 5 would be 10 times 10 times 10 is 1,000. So somebody just asked about a base. I think was it you? So this is basically what we're doing here. This says the hydroxide ion concentration in the soil sample was 5 times 10 to the negative 7. We need to find the pH. And the pH is negative log of H3O plus, which we are not directly given. So we have to find it. We are told OH minus equals 5 times 10 to the negative 7 molar. We have to find H3O plus. But we know that is 10 to the negative 14 divided by that. Somebody do this for me. Let's just come on.
Negative 27.
I got -8.
Yeah, negative 8 seems right. 2e negative 8, which is 2 times 10 to the negative 8. So that is my H3O plus.
So, yeah, find that you just.
So I'll take the negative log of that to get my pH.
Okay, so you just put the whole equation they give you to the equation.
Oh, because you had regular 7 and not negative 7, that's all.
Oh, so the number they gave us was an OH minus concentration. But in order to find pH, we have to know the H3O plus concentration. So we go back to the first thing we did, solve for it, and we get 2 times 10 to the negative 8. So now we take the negative log of 2 times 10 to the negative 8, and that equals 7.7. So if my pH is 7.7, acidic, basic, or neutral? Basic. Larger than 7 is basic. You say, but it's still 7?
So if it's larger than 7.0.
Right, so 7.0 is neutral. So 7.1, 7.05, that's larger than 7, so it's basic. Let's take our break. Who wants a 10-minute break? Who wants a 15-minute break?
10.
Who wants a 10? 10? Does anybody want a 15? Presumably. No guarantees. Let's do a 10-minute break. We'll start at 25 after on that clock.
Do you have cash?
be, let me find one. Lecture is 11, 12, 13. Today's is 13. Last week's was 12. The little bit we went over after the last exam was 11.
Do we have lecture after Tuesday's class? After Tuesday?
We have lecture meeting, but we won't have a lecture. We'll still meet here, but it won't be a lecture.
No, after the exam.
Oh, yes. But it's not a lecture. We'll do stuff. We'll do a review, but it's not a lecture.
Okay, so it's like a review on that.
Yes.
Okay.
Because I wasn't sure if it was several people.
There's one more at the very end. That's not for me. So we're going to take what we just did, and we have some solutions here, and we have to figure out the pH of our solution. So the first one is 0.00085 HCl. As before, the first thing I would suggest you do is figure out, is my solution an acid or a base? Is it an acid or a base? It's an acid. Hydrochloric acid, HCl. So, the number that we're given here is going to tell us our H3O plus, because it's an acid. How many hydrogen are in each HCl? 1. And so, that number that I'm given is my H3O plus concentration, or 0.00085. That is my H3O plus. The question is asking, what is the pH of the solution? Do we have to do anything else before we can solve for our pH? Say it again. In this case, no. Because to find pH, you just take negative log of H3O plus. And we have that. So we take the negative log of that. What does that come out to be? Negative log of 0.00085. 3.07. The last little bit of the question says, check your answer to make sense. And we'll never know whether we have the exact right number. But occasionally we can catch that we have a completely wrong number. So based on this pH, is our solution acidic, neutral, or basic? Negative log of that?
Oh, okay.
And so, is that acidic, neutral, or basic? Acidic. Considering the fact that we added HCl, would you expect your solution to be acidic, neutral, or basic? Acidic. We added HCl. We added an acid. And so you would expect the solution to be acidic. And it is. If you did your calculation and you got 10, then you could say, I must have done something wrong. Because my pH is telling me I have a basic solution, but I added an acid. And so I must be wrong. So we'll do the next one. We have 0.01 molar NaOH. Is NaOH an acid or a base? It's a base. So this one we will have to do some extra work. In this case, our OH minus concentration is 0.0101. We cannot calculate pH from that. We have to turn it into H3O plus. And so, H3O plus is 1 times 10 to the negative 14 divided by that equals 1 times 10 to the negative 12. I have a base, 0.01. Because it's a base, that's telling me my OH minus concentration is 0.01. But I can't use that to calculate pH. I have to convert that over to my H3O plus. So H3O plus was Kw divided by OH minus. So my H3O plus is 1 times 10 to the negative 12. So pH is the negative log of that, which is 12. Yes?
So when you do the negative log, it's always in the context of H3O plus?
Until we get to the next slide. So here, our pH was 12. Is a pH 12 acidic, neutral, or basic? Basic. We added a base, so it makes sense. Our last one, we have 1 molar H2SO4. H2SO4, an acid or base? Acid. What is my H3O plus concentration? 2. Sulfuric acid concentration is 1, but just 2 hydrogens for each one. Each of these gives me 2 hydrogens. So I go 1 times 2 is 2 molar H3O plus. And so negative log of 2, that was negative 0.3, I think, when we did it before. Yes, that's an acid. That's sulfuric acid. And so again, it makes sense. We are less than 7, so it's acidic, and it's an acid. So it makes sense. For the most part, if it has an OH, it's a base. I think the only base you will see in a problem like this, actually, if they're asking you about pH, if it's a base, it will have OH minus. They would never give you a pH type problem with a base that it does not have OH in it. And it would have an H on the front of it if it's an acid. So getting back to Jonathan's question. Here we're calculating pH. We're calculating pH. To get pH, we take the negative log of the H3O+. There's also such a thing as POH, but it's the same exact equation, but instead of negative log of H3O+, it's negative log of OH minus. And yes, it adds one more thing, but adding this one more thing is going to simplify a lot, and you'll see how that works. So POH, negative log of the hydroxide ion concentration. Because of the whole OH minus times H3O plus equals 10 to the negative 14, remember when we said the exponents have to equal negative 14? That means the pH and the POH put them together have to equal 14. So if I have a pH of 4, my POH is 10. If I have a POH of 1, my pH is 13.
Oh my god, that makes no sense.
It does, doesn't it?
pH, POH. That makes no sense.
So, this is really easy math. If they're whole numbers, you can do it in your head. If they are not whole numbers, if they're decimals, you may have to do it in your calculator, but it's a whole lot easier than doing scientific notation. Yes, okay.
So if we were given, like one of the last problems, if we were given the base.
Like if you were given a concentration like this?
Yeah, and so we don't have to go back and do the whole like K.
Correct.
Just use that one.
So we'll see that. And so there's going to be multiple ways we can get from point A to point D. We can go through B or C. And one of them, using this, is going to be a lot easier than what we were doing.
Can you go back to the previous slide one more time?
That one?
No, the previous one.
That one.
You said that number 2 was that
It's base.
basic?
Yes.
It was basic?
Yes.
And
Yeah.
then the last one was acidic?
Acidic. So here, this is how we undo pH and POH. So to go from H3O plus to pH, we do negative log of our H3O plus. But we can undo that in our calculator. And the way we undo that is we take 10 to the negative pH. 10 to the negative pH gives us H3O plus. If we have our POH, we can go 10 to the negative POH and go backwards to OH minus. And that is a pretty easy thing to put into your calculator. So if we take another soil sample and we figure out the pH is 6.2, the question is asking us, what is the H3O plus concentration? And it's simple. We just go 10 to the negative 6.2. You can't leave an exponent as a decimal. If it was just 10 to the negative 6, you could leave it be. But you have to have whole numbers up here. And so what you put in your calculator is just 10 to the negative 6, hit enter. And it's going to tell you something. What is it?
Not 6.2? You don't put 6.2?
Yeah,
Yeah,
What?
10 to the negative 6.2
Okay. So it equals 6.3095.
times 10 to the
Yeah, negative 7.
negative 7. And so that's literally, you just go 10 to the negative 6.2, enter.
Wait, I thought you just said you can't put decimals.
You can't leave that as your answer. You can put it in your calculator, but you cannot circle that and tell me that is your answer on a quiz. You have to convert it because your exponent has to be a whole number, and your calculator does that for you when you just put that in and hit enter. So looking at the pictures, those are hydrangeas. Does anybody ever put coffee grounds? Does anybody grow hydrangeas?
No, but I know that their acidity has something to do with their color.
Yeah. And so the acidity of the ground hydrangeas are grown in helps determine their color. And so the top picture with the A underneath, it's a blue hydrangea grown in acidic dirt. On the bottom is a more pink hydrangea grown in a basic soil.
So the blue ones would have the coffee grounds because coffee
Is acidic, yes. So some people will take coffee grounds and put it underneath their hydrangeas to acidify the ground, and it makes their hydrangeas blue. Yeah.
So the 6.3 times 10 to the negative 7 is the concentration?
That's your concentration of your H3O plus. Yeah. So now what we have is we have a toolbox of equations. We have 4 things that we can solve for. We have H3O plus, OH minus, pH, and POH. If you are given one of them, you can find the other 3. And you will have to do that. And so you can be given any of the 4. Let's say we're given pH. We can easily find POH. We can easily find H3O plus. To get to OH minus, we have to do 2 steps. And like Catherine was pointing out, we can either do that, and then go from that to that, which we know how to do, but it's more complicated. I have to do one of these vertical steps. I have to go from either POH to OH minus, or PH to H3O plus, and the level of difficulty in both is exactly the same. It's just 10 to the negative this. But I have to choose whether I want to go this way or that way. I can either go like that or like that. To me, this step, pH plus POH equals 14, is easier than that top one. I never, ever, ever do that top step. It's asking for calculator errors. And so, I would go this way. If I was given that, I would go from there to here to here to there.
So basically you're avoiding the top one at all costs.
Yes, I avoid the top one at all costs.
I think this chart makes it like really easy.
You don't have to use this chart. It's just showing that we've learned all these things and they're all connected. We can be given one of them and we're able to find the other 3. Yes?
So, how would like a question say like, it gives you the POH? Like what would it say? It would just say POH is?
Yeah. What you'll see on the homework and then the quiz is a table with 4 rows, and each row is giving you one of these. And so you'll have to start on all 4 corners. Say it again? Is this on the cheat sheet? No. This is not on the cheat sheet. So here we have a lake, and it says if the pH of a lake falls below 4.5, the lake is considered dead, because nothing can grow in a lake that's more acidic than pH 4.5.
This is the last thing we learned today.
No. So we send somebody out. How many people have done water testing when they're in elementary school, middle school? You did pH. pH was one of the things you measured, I'm sure, unless you were not in the pH group. Here, apparently, they went out and their pH meter was broken or something. And so instead of H3O plus concentration, they measured OH minus concentration. They made it as difficult for themselves as possible. And so we know our OH minus concentration is 10 to the negative 9. That is our OH minus. The question says, would this lake be considered dead? To figure out whether it's dead, we need to know the pH. Because we have to figure out if it's above or below 4.5. So I'm going to go back to here, and we're going to go from that corner to this corner. Again, I avoid that top side. So I would go from OH minus to POH, which is easy. Take the negative log of that. Negative log of that is 9. And so the pOH of our water is 9. pH is going to be whatever 9 needs to get to 14. So 14 minus 9 equals 5. My pH is 5. To go from pH to H3O plus, I go 10 to the negative pH, which is 10 to the negative 5 molar. And I'm done. Yeah. The pH plus pOH equals 14. And so because 5 plus pOH equals 14, I'm solving it for pOH. That was there. The pH plus the pOH add up to be 14. So that is about the most complicated problem you can do. The only thing you could add to make it more complicated is rather than simply being 1 times 10 to the negative 19, putting a coefficient like 3 times 10 to the negative 8, something like that. The math isn't any more difficult. The steps aren't more difficult. You just have to do it in your calculator instead of your head. Where?
On the left, down, back, right behind you.
That?
Yeah.
Yes, that's a 5. Yes, that's an M. And
This is
so,
our actual answer.
so our pH question is asking about whether the lake is dead.
Right.
And so I need my pH. So I'll come back, my pH was 5.
Okay.
Below 4.5 is dead. Is my lake dead? No,
Wait, so why did we do the last step?
because I got carried away.
Okay. I'm like, you're losing me today. I don't know what's going on.
Why did we go pH to PO?
Why do we do that?
No, over there.
Here?
Why did we carry on?
Because we went from that to that. We had to go from here to here.
Oh, okay.
On our chart, we started here, we had to get to here. So we went from here to here, and then here to here.
You do need the chart. You said I don't need the chart. You have to.
You don't, you have to live the chart. You don't have to memorize the chart.
Okay. I don't think.
So our lake is not dead, but I wouldn't necessarily want to go swimming in. We can measure pH a number of different ways. How many people have a pool? Or an aquarium where you have to measure the pH? How many people have, nobody's measured pH before?
I made on my tongue.
You what?
On my tongue.
Measure the pH of your tongue?
I would like your saliva.
For what reason?
Some people think that pH in your body determines then you're gonna get cancer.
So people who have people who have measured pH, when you measure the pH of your tongue, how did you measure it?
You just like put the little strip like
So you had the strips.
yeah.
I guess if you're measuring your tongue, the other ones don't work very well. Litmus paper is there are two different types of strips.
I guess I have done it.
So
Completely.
this is these strips where you put the strip. There's four different little patches here. You dip it in your solution and it changes color. Then you compare it to the container, in whichever set matches your set tells you the pH. And so it would say this is pH 7. If your strip matches that, it's pH 7. Litmus paper doesn't tell you pH, it just tells you acid or base. And so I don't remember which one's which, but there's a blue strip, you put it in, if it's one or the other, it turns pink. There's a pink strip, you put it in acid, it turns blue. Something like that. There's also liquid indicators. I think with people with pools, a lot of times will use the liquid. I've never had a pool, but it's the same idea. You put the pH indicators in the water, and you get colors. You compare it to a standard. But in a real lab, you have a pH indicator. It's just an electric machine. You stick the little probe in your solution, and it tells you the pH. Whole lot easier. But, of course, these cost a lot more money than that. Remember a few weeks ago when we were doing the reactions lab, you had a reaction where you added phenolphthalein to it. When you dropped the base in, it turned pink, and you swirled it and it went back clear. Remember that? Phenolphthalein is what we call a pH indicator. If phenolphthalein, which is this crazy looking molecule here, if it's in an acid, it has no color. But when it's in a basic solution, see how this breaks apart here? It's now essentially a different molecule. And this molecule is pink. So you put the phenolphthalein in your solution, and depending on whether your solution is clear or pink, you know whether it's acidic or basic. And there are a lot of these different dyes. Phenolphthalein is just one of them. So this is essentially what you did. You had an acidic solution, and you dropped the base in. As you dropped the base in, it would turn pink, and then you'd swirl it, and it would react with all the acid around it, and so the pink would go away. And eventually you added enough that you used up all of the acid. The next drop you added turned it a little pink, and then when you added a little more, it turned dark pink. So there, like I said, there are a bunch of them. These are all different pH dyes. If you're using these, what you do is you look for the pH range that you're dealing with. So phenolphthalein is here. That color change is around pH 10. 10 is where it changes. And so if you were trying to figure out whether your solution was pH 3 or pH 4, phenolphthalein is not going to work for you, because it will just stay clear. And so if you want to figure out whether it's 3 or 4, you would probably use this methyl orange. So it changes from red to orange to yellow around 3 to 4. This reaction of an acid with a base is called titration. HCl is an acid. If you react it with a base, you get a salt, an ionic compound, plus water, always. An acid plus a base gives an ionic compound plus water. It's not always this easy, but for you it will be. You can calculate how much of an acid you need to completely react with a certain amount of base. And it's an easy equation. Concentration of one times the volume of it equals the concentration of the other times its volume. So the concentration of the acid times the volume of the acid equals the concentration of the base times the volume of the base. We're going to skip this slide. You don't have to actually calculate titrations. Great. You're welcome.
So it won't be on the exam,
No.
but possibly the final.
I don't know.
No, you don't know, or you don't.
Have you found out yet if they're redoing the final?
No.
So we don't know.
So I don't know.
Okay. Just putting it out on the exam.
So we're going to now come to buffers. Okay. A buffer is a combination of a weak acid and a weak base. Sorry, a weak acid and a conjugate base, or a weak base and its conjugate acid. You will always be that combination, and they'll roughly be in about equal concentrations. A buffer is designed to prevent pH change. If you have a buffer and you add an acid to it, normally the pH, if you have just a normal solution and you add acid, the pH would change a lot. If you add acid to a buffer, the pH change is very small. The main buffer system in our blood is what's called the bicarbonate buffer system.
So you said it's designed to do what?
Prevent pH change. And so this is our example buffer. It's the bicarbonate buffer. We have carbonic acid, H2CO3, and its conjugate base, bicarbonate. The bicarbonate ion, they're different by one hydrogen. To make a buffer, you need two things that are different by one hydrogen. If they're different by more than one hydrogen, they will not be a buffer. If they have something else different about them, whether this changes to a phosphorus, that's not a buffer. They can only be one hydrogen apart. So if we take carbonic acid and we mix it with an equal amount of bicarbonate, we have our buffer. So it's sitting here, we have equal amounts of each. If we come along and we add an acid to it, that's what this means with the, when acid is over our yields arrow, that means we're adding acid. That acid is going to react with our base. This bicarbonate is our base in our buffer. And so it reacts with this. When it reacts with that, it makes more of that. And so we're now out of balance. We now do have more acid than we have base. So our pH did change a little bit. But this acid that we added here was a strong acid. And a strong acid should make the pH change a lot. Essentially what we did is we added a strong acid and converted it to a weak acid. We got rid of our strong acid, but our weak acid level went up. But a weak acid is not going to have as large of an effect as our strong acid. If we come back to neutral, and we add a base, it's going to react with our acid, and so this level goes down, and we make more of that. We now have more of our base, but it's a weak base. We convert the strong base that we added into a weak base. And so the pH change didn't go, the pH didn't go up by very much.
So what is the OH?
The OH reacted with the acid in our buffer, which is our carbonic acid here. So this reacted with that to make the bicarbonate, the blue. The hydroxide reacted with the red to make blue. The red went down, the blue went up. But if you measured the pH would not have changed very much in either of these. Whereas if you added the acid or base to pure water, it would have changed a lot.
So is OH the buffer?
OH is a base. The buffer is these two things combined.
Okay.
That is our buffer system, is those two things together.
This is two separate equations, though, correct?
What do you mean? We're starting here, and we can either go that way or that way.
Okay, I see, okay.
You wouldn't go from here to there.
Okay.
So, we're going to have to figure out whether these things can be used to make a buffer. Remember, we're looking for two things that are different by one hydrogen only. Are these two things different by one hydrogen only? No. They're very different things. So these cannot make a buffer. What about this? Is there one hydrogen different between them? Yes. This hydrogen here got replaced by a sodium. You may also see, instead of having the sodium there, you may just have CH3CO2 minus. So then it would probably be even more obvious that it was different by one hydrogen. The hydrogen on the end went away and it got just replaced by a negative charge. What about the last one? Yes. So there's one hydrogen different. That's the first thing we have to look for. But the other part of the definition was a weak acid in its conjugate base or a weak base in its conjugate acid. So our acid here is hydrobromic acid. Now we have to go all the way back to the beginning of the lecture and even the video. Is hydrobromic acid a strong acid or a weak acid? It's strong. Hydrogen with a halogen is a strong acid. So even though these are different by one hydrogen, they cannot make a buffer because it's a strong acid rather than a weak acid. So, like I mentioned, our body pH is mostly controlled by that bicarbonate buffer system. Sometimes that pH gets out of whack. Normal pH in our body is about 7.4. We say physiological pH is 7.4. If your blood gets more acidic than 7.4, we say that you're suffering from acidosis. And it's important to notice if it's more acidic than 7.4. So 7.1 is acidosis. But 7.1 is actually a basic solution. So here, we're kind of resetting our benchmark. If you're dealing with the body, instead of 7.0, it's 7.4. So acidosis is pH less than 7.4. And if your pH in your blood is wrong, the pH in your cells is going to be wrong. And all of the enzymes in your body are made to work at a specific pH. If the pH is wrong, the enzymes won't work right. And everything that happens in your body is due to enzymes. So if the enzymes in your body aren't working right, everything in your body stops working right. We have seizures, diarrhea, all kinds of brain disorders, shortness of breath, heart rate, vomiting. It's not something you want to deal with. So here is how we control that pH. We have carbonic acid in the middle here, and this is saying it's in equilibrium with this, and it's in equilibrium with that. So if we have carbonic acid in our blood, carbonic acid breaks down into CO2 in water. We can make carbonic acid with H+ and bicarbonate ion. If we're here, we come over here, we make CO2. What process in your body immediately should jump to mind if you talk about CO2? Lungs, breathing. If I breathe out, since you were in elementary school, you knew that you breathe out carbon dioxide. You know you breathe out carbon dioxide, right?
I did not know that in elementary school.
Well, I don't remember. Maybe it wasn't elementary school. I don't know.
pH in elementary
No, but you knew at some point when you were young, you learned that you breathe out carbon dioxide, you breathe in oxygen. Did you breathe out carbon dioxide? Think of this as the equilibrium. If you're getting rid of CO2, what happens to the equilibrium? Does it shift this way or that way? When you remove something, it shifts towards it. And so if I breathe out CO2, I'm getting rid of acid. Kidneys make bicarbonate ions. That's one of the things that they do. So your kidneys can get rid of acid by making bicarbonate ions. So if you have acidosis, they call you acidotic. That's the adjective. Okay, acidosis is the disease, I suppose. In the adjective, if I say I have acidosis, I am acidotic. So pH is less than 7.4. There are two types of acidosis. First is respiratory. Respiratory acidosis means you have acidosis because your lungs aren't working correctly. If we look at this, if we have too much acid, that means we are not getting rid of enough CO2. Why would you not be breathing out enough CO2? Such as? Why would I not be?
A lung collapses.
A lung collapses. Your lungs could just stop working, right? Why else would you not be exhaling enough CO2? Dead. You could be
Because
dead.
you stopped breathing.
You could stop breathing.
What, asthma?
Asthma.
Because you were choking and somebody didn't do the
Yeah.
hygiene yet.
Or if you have a cold and you have all kinds of stuff in your lungs. How many people have had pneumonia? You probably were breathing pretty heavy, right? Because you had a lot of stuff in your lungs blocking part of your lungs from working. And so if you only half your lungs are working, you have to breathe twice as fast to get rid of the same amount of CO2. There's also what we call metabolic acidosis. That's if your kidney does not make enough base, then the acid wins out. For respiratory acidosis, remember you're not exhaling enough CO2, metabolic acidosis. You're either not making enough of the base or you're making too much of the acid. When you exercise, when your cells make energy, they make acid. That's one of the reasons when you exercise, you breathe fast. Yes, you need more oxygen, but you're also making more CO2 that you have to exhale. So that's metabolic acidosis. Either you're making too much acid or your kidneys aren't working correctly. Alkalosis is the opposite. You would say you're alkalytic. pH higher than 7.4, again we have respiratory and metabolic alkalosis. If we have alkalosis, it's caused by our lungs. What does that mean? They're working too well, yes. The way I think about it is, if you're exhaling CO2, CO2 is acid. You're exhaling acid. If your blood is basic, you got rid of too much acid. And so you're hyperventilating. At least in TV shows, what do they show you people doing when they're hyperventilating? They breathe into a paper bag. Paper bag, please, not plastic bag. You breathe into a paper bag because you suffocate in a plastic bag.
What's the difference? I don't understand the difference.
They always say keep away from children because they inhale a plastic bag because it's too flimsy.
Oh, okay.
They just inhale it and they can't get it out. Presumably an adult wouldn't do that, but why try? So if you're exhaling too much CO2, you exhale it into the paper bag, but then when you breathe back in, you just take that CO2 back in. And so you stop losing your CO2.
What was the pH for acidosis?
That was less than 7.4. metabolic alkalosis. Either you're not producing enough acid, or more likely, your kidneys are overactive and they're producing too much base. So essentially your body has two mechanisms here. There's the breathing. Breathing is a short-term solution though. You don't want to have to breathe fast for the rest of your life to correct your pH. Your kidneys are the long-term solution. Breathing is the short-term solution. Other buffers in our body, we have a phosphate buffer in our blood. It's not nearly as important as the bicarbonate buffer though. And actually hemoglobin, the thing that carries the oxygen in our blood, also acts as a buffer. That's the end of lectures. But you now have an exam, a quiz, and a final exam. Plus 2 labs. So don't stop.